Welcome back to the first section of Chapter 10 and what is currently the new normal. We'll see how things work out with that, but as for now, this is how we do it. This is take 2. This time I'm going to try it without my microphone muted, see if the audio works out better that way. So Chapter 10 is on 3 dimensions. A lot of what we'll be doing in this chapter isn't particularly new. We've done it in 2 dimensions. We're just expanding it now to 3 dimensions. We'll be looking today at just the coordinate space, spheres. Later on, we'll get to vectors and things like that later in this chapter. There are a total of 4 sections in this chapter, so it's not a very long chapter, and we'll have a bit of time to get it done. So, as you can see by the picture, three-dimensional space and graphing is important because we live in a three-dimensional world. So the 2 dimensions is good for a lot of things because a lot of things we do 2-dimensionally, but there's also a lot of things that we do 3-dimensionally. So the first thing is 3-dimensional space. Instead of having just 2 axes, we have 3, which can actually be turned into 3 planes. We've got the x-axis is this one. This is the one that's actually sticking out at you, out off the page. And then the y-axis and the z-axis. Each of them has positive, and then the negative one's going to be back here. Y is positive, negative, z is positive, and negative down there. And so this is similar. We've actually saw this last year in Algebra 2 as well. So if we were to graph a point, we would not actually make all the planes. We would just make the axes that we were using, which would be the x, y, and z. So you'd start out with those guys, and then the x-axis kind of comes diagonal, and then it goes dotted back there. That's where we have it behind the screen, under the desk, things like that. And so this is x, y, and z. If we wanted to graph a point, let's say we wanted to graph the point 3, comma 1, comma negative 2, we would first, let's make the 3, or let's make our tick marks here. Graphing in 3 dimensions is not quite as much of a science as 2 dimensions. It's more of an art form, and it probably won't look perfect. But how we do it, so we're going to always start at the origin. We're going to go 3 in the x direction. So that would be 1, 2, 3. And now we need to move 1 in the y direction. That's this distance, but not starting there. We need to start at where we left off. And so we're just going to move 1 horizontally because the y-axis is horizontal. So we move a distance of about 1. And then 2 negative in the z direction. That's going to be this distance here. So we'd go down 2 that way. And that's where we'd put our point. So that's the point 3, 1, negative 2. The green stuff, like the trails, as I was graphing, that's not part of the point. That does not need to be there. It can definitely help us get to the right-ish spot. And it's also kind of like showing your work. So if you want that there, that is perfectly fine. But it doesn't have to be there. It's not part of the point. Now, what's weird about 3-dimensional graphing, especially if we don't have that trail there, is that this is not the only point that could be in that exact spot. This also looks like it could be x is 5, y is about 3, and z is 0. In fact, there's an infinite number of points. Like even if you graphed it perfectly on this 2-dimensional surface, there's an infinite number of points that would look like it's at the exact same spot. Basically, the line of points going from that point through your eyeball could all be graphed at about that same spot. So that's 3D space, that's graphing in 3 dimensions. the 3D space is also broken up with 2 dimensions. The axes break the graph into 4 quadrants. And we know these. This is quadrant 1, 2, 3, 4. Well, for 3 dimensions, we have those extra axes. It breaks it up into 8 pieces, which are called octants. So the 8 octants would be these ones. Now, they actually go in basically the same order as the quadrants. Octants 1, 2, 3, 4 are the same thing as quadrants 1, 2, 3, 4, where z is positive. Octants 5, 6, 7, 8 are the same as 1, 2, 3, 4, except z is negative. So like quadrant 1, x and y are positive, z is positive. Quadrant 2, x is negative, y is positive, z is positive. And then etc. Quadrant 7, they're all negative. And so sometimes it'll ask what quadrant it's in, and you can just see those. And again, it's the same as or what octant, it's the same as the quadrants, except that z is positive or negative. Distance and midpoint formulas. Just because we're in 3 dimensions doesn't mean we don't have distance and midpoints. The nice thing is if you had to take the 2-dimensional ones and turn them into 3-dimensional, chances are you would come up with exactly the same thing. So, midpoint for 2 dimensions. We find the average of the x's, the average of the y's. We were doing this even just last chapter. If we had the endpoints of a diameter of a circle, we'd have to find the center. And so, looking at this, if we had 2 points, let's say 3, 7, and 5, 12, the midpoint, we'd go 3 plus 5 is 8, divided by 2 is 4. And that should not be a surprise that 4 is halfway in between 3 and 5. When we have something like 7 and 12, it's a little bit more difficult. 7 plus 12 is 19, divided by 2 is going to be 19 halves, or 9 and a half. Which is a little bit harder to just kind of eyeball and know that, oh yeah, 9 and a half is right in between 7 and 12. That's why the formula kind of works out. So that's 2-dimensional. If we want 3-dimensional, we do the same thing, we just have z as well, because we have that ordered triplet instead of an ordered pair. So if we have a couple points, let's say 2, -1, 7, and 8, 3, 2. We're going to do the same thing. 2 plus 8 is 10, divided by 2 is 5. -1 plus 3 is 2, divided by 2 is 1. And 7 plus 2 is 9, divided by 2 is 9 halves, which could also be 4 and a half if you wanted to go that way. But that would be the midpoint between these 2 points. So it's the exact same thing you do with 2 dimensions, except you have to do it with the z as well. Distance works out basically the same. The distance formula, x minus x squared plus y minus y squared, big square root. Same thing, except we also have the z's in there as well. So let's find the same, use the same points. Let's go the distance here. So we'll have a square root. We'll have a 8 minus 2 squared plus 3 minus -1, which would be 3 plus 1 squared, plus 2 minus 7 squared. And the nice thing about this is it doesn't matter what order you're in. You can even switch the orders, because the only thing that's going to change is the that sign. When you square it, it's all going to be positive anyway. So it makes it even harder to mess up. 8 minus 2 is going to be 6 squared, plus 3 plus 1 is 4 squared, plus 2 minus 7 is -5. When we square it, it'll be positive anyway, so we'll just go 5 squared. That way you don't do something horrible like putting negative 5 squared into your calculator and get negative 25, because we all know that that's not good. 6 squared is 36, 4 squared is 16, 5 squared is 25. We can add these together. 36 plus 16 is 52, plus 25 is 77. So we get the square root of 77. Very frequently, these will not simplify down to a nice whole number. Sometimes they do, sometimes they don't when we have just regular distance in 2 dimensions. Rarely will these simplify to a whole number in 3 dimensions. It is possible to simplify it a little bit, but not in this case, because this is 7 and 11. They're both prime, so that is where it is. Next piece, standard form of the equation of a sphere. I really could have faded this in now that I'm doing the retake on this, but I forgot to do that, so it will sit there and wait. Let's see if I can remember to do it before going on to the next slide this time, however. So, equation for the standard form for the equation of a sphere, just like everything else, this is a direct extension of 2 dimensions. 2-dimensional, we have a circle. The equation of a circle with a center at hk and a radius of r is going to be x minus h squared plus y minus k squared equals r squared. We just got done doing that last chapter. So for a sphere, we're going to center it at hkj. Why do we use j? Because it's the letter that comes after k. The radius equals r, and so it's going to be the same thing, x minus h squared plus y minus k squared plus z minus j squared equals r squared. One of the mistakes people make on this is they try to go with a cubed on something. It's all squared. The sphere, it's not like a solid ball, it's only the outside. It's an area type thing, so it's squared. If we did want the whole thing all the way to the center, like the Earth is a sphere, we want to consider the whole Earth and not just the crust, we'd go, it's all less than or equal to r squared. And that would get us everything. When we get volumes, that's when we get cubes. So that's a sphere. If we wanted to write the equation, if we had a center and a radius, we just plug it right in. But more exciting, find the center and radius of the sphere. In order to do this, we're going to have to write the equation of the sphere, and then it'll be right in the equation. So how do we change this into the equation of a sphere? Oh, did someone say completing the square? Yeah, you know that thing we worked on a lot last chapter? It's still here. The nice thing is it's still exactly the same. So let's complete the square here. We're going to start out by grouping the x's, the y's, and the z's. So we'll have 2x squared minus 2x, and then leave a space, plus 2y squared minus 6y, leave a space, plus 2z squared minus 4z, and then we'll move the 5 over to the other side. Oh, we need to factor out those 2's. So, fun story, if you are doing other conic sections, they also translate exactly just like the circle does to the sphere. You get ellipsoids. Those are really nice, super easy, like it makes sense. The hyperboloids and paraboloids are, the equations translate perfectly, but they're a little bit tougher to like imagine in your head. But the ellipses, though, perfect translation there. So we're going to factor out the 2. So we have 2 x squared minus x, leave a space, plus 2 y squared minus 3y, leave a space, plus 2 z squared minus 2z, leave a space, equals negative 5. Now we can complete the square, so we'll have 2 times something squared plus 2 times something squared. Well, this will be an x, this will be a y, plus 2 times z something squared will equal something. I don't have much space over there. We'll figure that out. So First one, the x's, we divide by 2. Well, that's -1, so that'll be a -1/2 squared is plus 1/4. We have to add to the other side, but we don't add 1/4. It's 2 times 1/4, which will be plus 1/2. For the y's, -3 divided by 2 is -3/2 squared plus 9/4 times 2 will be plus 9/2. And then for the z's, divide by 2 is -1, so that's plus 1 times 2 is plus 2. We had that -5 up there. I'm just moving it down because I don't have the space off to the side. -5, so 1/2 plus 9/2 is 10/2, which conveniently is 5, plus -5 is 0. So that makes this equal to 2. Almost done, but we don't want these 2's, so we're just going to have to divide everything by 2 to get x minus 1/2 squared plus y minus 3/2 squared plus z minus 1 squared equals 1. And so our center, because that's what the question's asking, center and radius, center would be 1/2, comma 3/2, comma 1, and the radius equals the square root of 1, which is 1. So that's how we can find the center and the radius and just write it in standard form. It's the same thing we've been doing all last chapter. Finally, the trace of a surface. Now, a trace of a surface is where we just take one little cross section. Generally speaking, when we will do it, it'll be on one of those planes, like the XY plane, the YZ plane, the XZ plane. So it'll be on one of those, and it's just where does it intersect that plane. So it's kind of like an intersection. In fact, that's also how we find it. So to do this, we're going to sketch the XY trace of the sphere given by x minus 3 squared plus y minus 2 squared plus z plus 4 squared equals 5 squared. So the XY trace, that's going to be on the XY plane. What every point on the XY plane has in common, z equals 0. On the YZ plane, x equals 0. On the XZ plane, y equals 0. Whatever one is not here will equal 0. So all we're going to do is we're going to plug this in and then simplify. So we'll have x minus 3 squared plus y minus 2 squared plus 0 plus 4 squared equals 5 squared, which is 25. These aren't going to change. Just x minus 3 squared plus y minus 2 squared plus 4 squared is 16 equals 25. Subtract it over. X minus 3 squared plus y minus 2 squared equals 9. So this would be a circle with a center of 3, 2, and a radius of 3. To sketch it, we would have our axes. I don't have enough room here. I'll actually show you a good picture of this as well. Then we're going to start out with our center, 3, 2, 1, 2, 3, 1, 2. The center will be about here. And then we'd go over 3, over 3, over 3. This way will take us about there, over 3 here. And then we make our circle. If my pen would actually work here. Oh, there it goes. It all came at once. And so that's kind of what it looks like. It's on there. Now, what does it actually look like? We have a sphere, and we're just taking this cross section where it's right here at the, right there at the, at that plane, and that's the part that we're looking at. So, most of this stuff, again, is just an extension from what we've been doing. A lot of it we've actually seen before, but um, not necessarily this year. So this is the first topic of the 4. Um, until next time, keep working problems, keep asking questions, and as always, happy mathing.